start. And it's a great pleasure to introduce Professor David Wright from Washington University in the United States. Professor Wright is going to talk about the Jacobian conjecture through the lens of formal inverse and combinatorics. So please.
Thank you, Francisco, for inviting me, and it's good to see everybody. A few of you I know, but not many of you, so nice to meet you. And I have to say this is the first time I've ever presented at a virtual math conference, so we'll see how this goes. I did practice sharing my screen, so I'm going to do that now. And I'm going to go through a slide presentation. And I also included that presentation in the chat. So if you want to download what I'm about to show you, you can do that. And if you're interested, all you have to do is press the three little dots to the right of that, and it'll allow you to download it. So at this time, I will share my screen. Hopefully this works. And you are looking at my desktop right now. So I'll blow that up. And so there you see the title of the talk, which you just heard. And let me just say that this, looking at the Jacobian conjecture using formal inverse and combinatorics is not a new approach at all. It goes back over 40 years, perhaps beginning with a paper by Bass, Cannell, and myself from the late 70s or early 80s that is often referenced. So I will present one approach, one combinatorial approach to it, but I acknowledge there are others. And for the most part, this is a survey, but there is one new twist at the end. And in the process, I will tell you, what are the strengths and the glaring weaknesses of looking at the Jacobian conjecture through this lens. So I'm going to give a setup here that'll be ironclad throughout this talk. I consider a polynomial map f from Cn to Cn having the form f equals, now this is a vector equation, f equals x minus h. Why do we write minus? Well, because the formulas work out better that way. With h having order greater than or equal to 2, by order I mean that the degree of its lowest degree homogeneous summand is greater than or equal to 2. That's what I mean by the order. So writing things out in detail, f has coordinate functions f1 to fn, where fi is xi being indeterminate, minus hi a polynomial in variables x1 to xn, homogeneous summands of degree greater than or equal to 2. So later we will be assuming h, in other words, each hi, is homogeneous of a fixed degree d greater than or equal to 2. And in that case, by slight abuse of language, I will say that f is of homogeneous type. And if that degree of h is d, we say f is of d homogeneous type. And I'm an algebraist, so I view f1, fn as elements of the polynomial ring C bracket x1 to xn. They, rather than actual functions, they determine functions. And of course, you are uniquely given by the function they determine, since we're over the complex numbers. But I see polynomials. And then for any map f, we have the Jacobian matrix. I write it as J of f. So it's that matrix specifically that you see in front of you. D1 F1 up to Dn Fn, D1 Fn up to Dn Fn. Dj means the jth partial derivative. And I simply write Det in front of it for its determinant. And I view J of f, the Jacobian matrix, as a matrix with entries in the polynomial ring. And its determinant, therefore, is an element of the polynomial ring. So now let's f equals x minus h is going to be fixed throughout this talk. So the Jacobian conjecture in this context can be stated: if the Jacobian determinant is 1, then f is invertible as a map from Cn to Cn. Determinant would be 1 if it's non-zero constant. If f is of this form, you can see that by just evaluating at the origin. And the term invertible, we know, is totally unambiguous. If f has any kind of an inverse at all, then it has a polynomial inverse. In fact, it suffices that f is injective. And these, of course, are non-trivial theorems, but I think you all are familiar with these facts. So I'll refer to the condition that the determinant of the Jacobian matrix is 1 as the Jacobian hypothesis. And it simply means that the Jacobian matrix is in the special linear group, meaning the group of matrices of determinant 1 over the polynomial ring Cx1 to Xn. Now, formal inverse, what do we mean by that? Sometimes called inversion. A polynomial map of this form has a formal inverse, F inverse, call it G, which has coordinates G1 to Gn that are formal power series. In other words, elements of the power series ring, C double bracket X1 to Xn. Now, don't think in terms of convergence. We don't worry about convergence. Just take a formal power series. And this formal inverse is uniquely defined by either of the conditions that G following F is the identity map, X1 to Xn, and F following G is the identity map. So either one of those uniquely determines G. And we'll write G of the form X plus N, as opposed to F, which was X minus H. Again, there's a reason for that, just for convenience, where all the homogeneous sum ends of N will, again, have to be greater than or equal to 2. So in this context, the Jacobian conjecture is not an existence problem anymore. It's not, does there exist an inverse? There is an inverse. But the question is whether or not that formal inverse is in fact a polynomial map. So the Jacobian conjecture asserts that if the Jacobian determinant is 1, then the formal inverse of G is a polynomial map. In other words, those coordinates G1 to Gn are actually polynomials. Okay. Now, where does combinatorics come into the picture? Well, they are used to describe the formal inverse. The formal inverse can be realized in various ways. And as I said before, there's more than one formula. But they all involve sums of polynomials with summands indexed by certain combinatorial objects called rooted trees. And I will discuss but one of these descriptions and explain why it is interesting and provocative in the study of the Jacobian conjecture, and I'll also explain why it has failed so far. So, what's a rooted tree? Well, it's a finite tree T, by which we mean a connected and simply connected graph, having a non-empty set of vertices denoted V of T, with one vertex designated as its root, denoted RT sub T. So for a vertex V, the height of V, denoted HT of V, is the number of edges in the unique geodesic connecting V with the root. And therefore, the height of the root is 0. And then for any V, we denote by V plus the set of children of V. What do we mean by that? It's the set of vertices that are connected to V by a single edge, but in the direction away from the root. In other words, the served vertices adjacent to V such that the height of W is 1 greater than the height of V. Now, given a rooted tree T, here's another concept that really comes into this picture. We have to consider alpha of T. That's the number of symmetries of T. In other words, the order of the group of root-preserving automorphisms of T. And then we write blackboard T for the set of root-preserving isomorphism classes of rooted trees. So that will be an infinite set. Okay, some examples of trees and symmetries. So we can have a tree like this one on the left. It's got, by the way, I always write the root at the bottom. I know that some combinatorials write trees with the root at the top, like a family tree, but I don't know. Somehow I got started writing at the bottom. I guess here in North America, trees grow up from the ground. So my roots are at the bottom. So there's the root, and we have 2 children. And you see that alpha of T is 2. There are 2 symmetries, the identity and the one that switches those 2. However, if I add one more vertex by giving one of the children a child, then you see there are no non-trivial symmetries because you can't switch these 2 children of the root anymore. Here's a more complicated tree. The root has 2 children, one of which has 2 children, the other which has 3 children. So how can you get a symmetry of that? Well, you can flip these 2 on the left, the 2 children, the 2 invertices on the left, and you can permute the 3 invertices on the right in any one of 6 ways. So alpha of t in this case is going to be 12. So I think that's pretty straightforward and allows you to understand what alpha of t is. Okay, I want to talk about labeled trees and how we get a polynomial out of a tree. So recall n, that's the number of variables in our system. T is a tree. I is an element of the set 1 to n, that's the number of variables. And I-rooted labeling of t in the set 1 to n is simply a function from the vertices into the set 1 to n. So it gives each vertex a label from 1 to n. And since it's I-rooted, we insist that the label of the root be I. Now, for a tree in T, blackboard T, an I-rooted labeling F, and a vertex V in T, and of course our system H1 to Hn, where F is x minus H. We write H sub V for simply H indexed by the label of V. So that makes sense to set labels from 1 to n. And we come up with a differential operator according to the children of V, namely the derivative, product of the derivatives corresponding to the labels of the children, W and V plus. So then we set P, the polynomial, T comma F, is the product over all vertices of the H's indexed by the vertices differentiated by the children. And finally, we suppress the F by just writing P sub T for the sum of all of these PTFs over all I-rated labelings F. And we refer to this as the tree polynomial for T. So that's how you get a polynomial out of a rooted tree. Okay, example. Well, suppose we have the tree, simply has a root and one child, that the root has got to be labeled I as an I-root labeling. And in this scenario, J, K, and L and all these summing from 1 to n. So I'll suppress the summation. So what's the polynomial look like? Well, we have HI from the root. It's differentiated by the child, J, so DJ, HJ from that vertex, and it's undifferentiated. Here we have 2 children of the root. So HI has 2 derivatives, DJ and K. HK from that is undifferentiated, and HJ is undifferentiated. One more example. Here we've got HI differentiated by J and K as above. HK is undifferentiated, but J vertex has a child, so HJ is differentiated by L. HL is undifferentiated. So I think that allows you to see how to form the tree polynomial given a tree. Okay, so again, there's our P of T. So it's the sum over all those labelings of what you see there. So again, F is x minus H as before. And now the formal inverse, now I explain what this has to do with formal inverse. Formal inverse, which is x plus n, is given by the following. X plus the sum of all the tree polynomials over all trees, where for each tree polynomial, you have to divide by the number of symmetries of that tree. You have to divide by alpha of t. So this will be the n that appears right there. G is x plus n. The n is given by the sum of these tree polynomials. And of course, that's an infinite sum, but it converges in the sense that the orders of these PTs go up with the number of vertices. And so you get higher and higher terms. So even in algebraic sense, not in any analytic sense, this sum converges as a power series. So it says in front of you for the next observation, we'll see that the order of P of T is always greater than or equal to 2. But you can see that right away. I'm actually going to suppress that. You can see that by looking at the number of edges, noticing that the number of edges in a tree is 1 less than the number of vertices, and you can write down what the order is. But let's just believe that for now, and let me go on past that slide. Now I want to consider the case that we're particularly interested in, and that is the case of homogeneous types, since we know the Jacobian conjecture is reduced to that. So F is x minus H now, where H is homogeneous of a fixed degree D greater than or equal to 2. And again, x plus n, G equals x plus n, is its formal inverse given by those tree polynomials. So it's well known that the Jacobian conjecture is reduced to this case with d equals 3. That's an old theorem of myself and Bass and Knitt. And that it is true for the case d equals 2. That's Wang's theorem. We know that the Jacobian conjecture is true in any dimension in degree 2. For H homogeneous of degree d, it's easy to see that P of t is homogeneous of the following degree. It's d minus 1 times the number of vertices plus 1. And that just follows from what I said. The number of edges, which will give you the number of derivatives, is 1 less than the number of vertices. So the summands of n, if you consider trees having a fixed number of vertices, those are going to give you the homogeneous summands of this gadget. So for a fixed number of vertices, that's the degree of the tree polynomial right there. So with that in mind, let's just sum over trees having r vertices for some fixed r and call that sum n sub r. So it's a subsum of the previous one, where we just sum over trees having r vertices, some of the tree polynomials divided by their number of symmetries. So we have g now as x plus n, but now we can write n in terms of homogeneous summands as n upper 1, n upper 2, and so on, with nr homogeneous of degree d minus 1 r, the number of vertices, plus 1. So this leads to yet another form of the Jacobian conjecture, and that is that if the Jacobian determinant is 1, then n upper r is 0 for r sufficiently large. That just says g is a polynomial. And so the question is, when should we expect nr to be 0? How far up do we have to go before we need to look for it to be 0 if the Jacobian conjecture is to be true? And that can be answered by the fact that there is a degree bound for the inverse. Most of you, I believe, know what that is. If we define the degree of a polynomial map, f, to be the maximum of the total degrees of the coordinate functions, f1 to fn, in the variables x1 to xn, then theorem of Gaber states that the inverse, if f is an automorphism of degree d, and if g is its inverse, then the degree of g is bounded by d to the n minus 1. So what does that say? In our situation, we have g as x plus n1 plus n upper 2, and so on, with n upper r homogeneous of degree d minus 1 r plus 1, and therefore, appealing to the degree bound, the minute d minus 1 times r plus 1 exceeds d to the n minus 1, we look for nr to be 0. And so f is going to be an automorphism if and only if that nr is 0 when this inequality is satisfied. And just solve that for r, and you get, that says r is greater than d to the n minus 1 over d minus 1. We can call that number capital R. That's going to be fixed in the rest of the talk. And of course, that's equal to 1 plus d squared up to d to the n minus 2. Okay, example. Let's suppose we're in dimension 3, degree 3. N is 3, d is 3. Well, you see, what does this read? This says 3 to 3 squared, which is 9 minus 1, which is 8. 3 minus 1 is 2. So 8 by 2 is 4. You get the magic number, capital R, is 4. So we expect n sub r to be 0 for r greater than 4. So if f is an automorphism, then g, the inverse, is x plus n1, n upper 1 up to n upper 4, and everything else has to be 0. Another case, n equals 4, d equals 2. We can see this gets big in a hurry because here r is 7, capital R is 7. So n upper r will be 0 for r greater than 7. So if f is an automorphism, then g is x plus n upper 1 up to n upper 7. So quite a few terms. Now, here's another question. How many n upper r's do we have to show are 0 before we're done? Do we have to show it for infinitely many, going up from capital R onto infinity? Well, the answer to that is no. There is a gap theorem that says if you're showing the formal inverse is a polynomial, you have to go up so far. But that formula is stronger by virtue of the theorem of Zhao, Wenhua Zhao, who, by the way, I believe is one of our speakers in this session, maybe not today. But he proved that in this context, we have n upper 1 is just h. And for r greater than or equal to 2, n upper r is 1 over r minus 1 times the sum where k and l add up to r and are both greater than or equal to 1. And now you have to stare at this to make sure it makes sense. You take the Jacobian matrix of n upper k, that's okay because that's a vector indexed from 1 to n, so it has a Jacobian matrix, times n upper l, that you can view as a column vector, and that will give you n upper r as a column vector. And from there, from that you see that if you have a gap that looks like this, if n upper m plus 1 is 0 all the way up to n upper 2m, if all those are 0 for some m, then you're done. Then you have to have n upper r 0 forevermore, because in proving that, using this formula, even one of the k or the either k or l has got to be bigger than m. So in particular, for our magic number r, defined as before, if we can show n capital R plus 1 up to n upper 2r equals 0, then we're done. And as a matter of fact, that's equivalent to showing the Jacobian conjecture. Now, I want to observe that in forming these tree polynomials, there's a heck of a lot of trees that you can ignore because they give 0. In particular, clustered trees. So let's suppose f is x minus h of d homogeneous type. So h is homogeneous of degree d. And note that if t is a rooted tree having a vertex b with more than d children, then p of t has to be 0 because it's got this factor, you're differentiating h sub v by the children. But if there's more than d children, h sub v is homogeneous of degree d, it's got to be 0. So if t has one or more such vertices, we say t is clustered, and by this remark, we can drop clustered trees from the summation that yields in. Those tree polynomials are all 0. So with that in mind, if the number of vertices is greater than our number r, which we wrote in this way, we have 0. So a non-clustered tree, if you think about it, forces the tree to have height at least n minus 1. Let's think about that. Whoops, I'm sorry, this thing keeps flipping without me giving it permission to. Let's form the lowest to the ground tree you can. We start with a root, so there's one vertex. Give it d children. You can't give it any more if you got a clustered tree. Give each of those d children, so that adds another d squared vertices. You get up to d to the n minus 2, and if you add one more vertex, you've got to have a tree that has height n minus 1. You can't stack any more down low without having a clustered tree. So this forces a non-clustered tree, in other words, a tree with a non-zero tree polynomial, to have height at least n minus 1. Now, this turns out to be provocative for a reason that I will come to in a minute or two. So now, I want to study the Jacobian hypothesis in the D homogeneous case. So we have Jacobian matrix of F, it's Jacobian matrix of X minus H. So that's the identity matrix minus the Jacobian matrix of H. And of course, J of H is that matrix you see in front of you right there. Stop that. Since H is homogeneous of degree D, its Jacobian matrix is a homogeneous matrix of degree D minus 1, which is greater than or equal to 1, since D is greater than or equal to 2. And it follows that JH is a nilpotent matrix. That's just a fact. In any graded ring, if you have 1 plus a homogeneous element being invertible, that homogeneous element has to be nilpotent. And then once we know it's nilpotent, well, by linear algebra, we know that its nth power has to be 0. So JH to the n is 0. And thus we have, for a fixed I naught In, this product, well, what is that? That's just the I naught Inth entry of JH to the n, where you sum over these indices. That's just the way you multiply matrices. So this thing has got to be 0. That looks provocatively like a certain tree polynomial. Let's consider a geodesic with n vertices. So its height, therefore, is n minus 1, has n minus 1 edges. And keeping in mind that product, which you saw on the previous page, that's 0. Now, let's consider this tree. And so just start writing down its tree polynomial. So you've got hi naught differentiated by I1, hi1 differentiated by I2, and so on. I'm sorry, I should be looking up here. And you get to the final one, hin minus 1 is not differentiated since that has no children. And this looks almost like that, except it's missing that derivative at the end. But we have homogeneous polynomials, so we can apply Euler's formula to a homogeneous form, which yields that hin minus 1 is 1 over d, its degree, sum in goes from 1 to n, xin, din of hin minus 1. So if we plug that in, right there for hn, then we get the asterisk, which is just our quantity up here, at least once you fix the nth coordinate, or in. And so that tree polynomial has got to be 0. So if you have a geodesic of height n minus 1, the tree polynomial is 0. And that's, we call that kind of the long geodesic principle, or more generally, the naked geodesic principle. If you have a naked geodesic whose length is the nilpotency order of the Jacobian matrix, that tree polynomial is always going to be 0. So now we see that trees that are too naked are 0, and trees that are too clustered yield 0. But we've got a lot of trees in between. So let's notice a case that everybody knows about, the case where the square of the Jacobian matrix is 0. The conjecture is true in that case. It's not too hard, but it falls out very easily from this discussion. Let's consider trees with one vertex. Well, it's just a root. So therefore, P of t for that tree is just h, viewing that as a vector h1 to hn. T2, how many trees with two vertices? Well, there it is, just one. And for that tree, you have P of t is equal to 0 by the long geodesic principle, since the square of the matrix is 0. So n1 is h, n upper 2 is 0. And then everything else got to be 0 by this gap principle. In m plus 1 up to m2n is 0, and we're done, but take m equals 1. We have n2 here and n2 there, and so nr has got to be 0 for r greater than 1. So, f inverse is just g equals x plus h. F is x minus h, f inverse is x plus h. That's when the Jacobian squares equal 0. So that's easy enough. Now, lest one gets euphoric, I want to point out that this kind of easy argument doesn't go much further. In fact, it breaks down real quick. And you're probably going to say, well, if it breaks down this quick, why are you bothering to look at it? And I'm not sure I have a good answer for that, but I will try to provide one before we're done here. So here's a failed calculation for, again, the d equals 2 case and n equals 3, a case where we know the conjecture is true by Wang's theorem. And here our magic number, capital R, dn minus 1 minus 1 over d minus 1 is 3. So what we need to show is that n4 equals n5 equals n6 equals 0, using the fact that the cube of the Jacobian matrix is 0. And we can consider trees only that are non-clustered, which since d is equal to 2, trees have to have less than or equal to 2 children. So here's a tree. This geodesic here, that one yields 0 by virtue of the long geodesic principle. Since the Jacobian cube is 0, that tree polynomial is 0. But now what about n4? N4 is the sum of 3 trees, non-clustered trees having 4 vertices. There's exactly 3 of them. That's the ones you see in front of you. So you have the polynomial of that T1, 1/2 the polynomial for T2. Why the 1/2? Well, because that tree has 2 symmetries, the identity and the one that switches those 2 children at the end. And P of T3 is going to be 0 again by the long geodesic principle, because the Jacobian to the 4th power is 0, since the Jacobian to the third power is 0. So actually, we just have these first 2 summations. Now, let's play this game. Let's consider that naked geodesic that we call T up here. And let's think of differentiating that by the label of that vertex. Okay. Well, this is a product, so you're differentiating it by hitting that, that, and that. So it's going to give you the sum of these tree polynomials. And it's going to tell you that that sum is 0. That gives P of T1 plus P of T2 plus P of T3. That sum's got to be 0, and the T3's got to be 0. But look, it doesn't quite give us what we need. It's that pesky little 1/2 that makes this method fail. And in fact, this is going to be 0 if and only if both P of T1 and P of T2 are 0. You can see that just by looking at those two linear equations. So the vanishing of N4 is equivalent to the vanishing of PT2 or PT1, but we can't really see that by looking at that picture. Sorry about that. And I should say that a similar dead end occurs if we try to calculate N5. But the method actually works to show that N6 equals 0 and N7. And, you know, I haven't chased it up too far because it gets really messy in a hurry. The number of trees proliferates. But I'm pretty sure the method probably works for higher ends. But what's missing here? There's something got to be missing because we need to see that that N4 and that N5 is 0. So what's the missing key step? So let's study the nilpotency conditions. Perhaps the conditions that we're looking at are too coarse to give enough information. And by the way, this is a new approach that I've been looking at very lately. It has not been studied in detail. Let's consider a generic n by n matrix, call it capital A with entries Aij. And again, being generic, I'm thinking of the Aij as being indeterminates in a polynomial ring C bracket Aij. So the nth power of A is given by Bij, which is the sum that you see right in front of you there. Ai naught I1, Ai naught I2, up to Ain minus 1 In, where I naught is I, In is J, and the rest of them sum, because that's exactly how you multiply matrices. So that's the ij entry in the nth power. That's got to be 0. So the equations Bij equals 0 determine the nilpotency of the matrix A. But looking at it as an algebraist, these do not generate the ideal I, remember what I is, in C Aij, of all functions vanishing on the nilpotent matrices. According to Hilbert's Null-Stellensatz, I is the radical of the ideal generated by Bij, and it's bigger than that ideal. You can see that immediately by considering the trace. There's a polynomial that vanishes over a nilpotent matrix. And you can see that it cannot be in the ideal generated by these Bij's, because this thing is homogeneous of degree n in these indeterminates, and that's homogeneous of degree 1. So there's no way it could be in that ideal. Okay, so the Bij's are maybe the wrong place to look. So what's the right place to look? What are the right nilpotency conditions? We look at the characteristic polynomial. Got some basic linear algebra going on here, folks. Characteristic polynomial chi, t is an indeterminate there. And there's the characteristic polynomial. It's the determinant of the addendity times t minus a, which is a monic polynomial of degree n in t, with these coefficients f1 to fn that are polynomials in the a's. Okay, so it's this determinant right here that you see in front of you. And you can see that the f1 is going to be minus the trace. The f2 is the sum of the principal 2 by 2 minors. ft is minus 1 to the t times the sum of all the principal t by t minor determinants. And fn is minus 1 to the n times the determinant of the matrix A. Now it turns out those f1, those f1 to fn are good generators for the ideal I that vanish on all nilpotent matrices. This is a theorem of Hochster. It's actually not published. He showed it to me at a conference many years ago. I took away the proof. Somebody should write it down, I guess. But amazingly, the polynomials f1 to fn do generate the ideal I, which we know is a radical ideal. But in fact, he also shows that I is a prime ideal. So that's the right set of nilpotency generators, but let's go back to our Jacobian situation. So maybe the thing to look at is what we get by specializing FT at the Jacobian matrix of our nilpotent matrix J of H. So we're plugging in dj of hi for aij in these polynomials. And this strategy, which is new, is use the vanishing of script f1 to fn and their derivatives to show that n upper R is 0 for R bigger than our magic capital R given by the degree band. Well, let me just say that this is new territory. The place to begin is in that place where I was stuck a minute ago, n equals 3 and d equals 2. And let me just say that I've just recently started thinking about this. I haven't even had time to chase that down to see if that can be done. But it doesn't look too difficult. And I think proving this would be a good thing. Now you say, why? Because we already know it's true for d equals 2. That's Wang's theorem. But on the other hand, Wang's theorem, there's various proofs of it. They end up proving the Jacobian conjecture for d equals 2 as long as the characteristic isn't 2. So it proves it in characteristic P for that case. Well, we know that all characteristics boil down to the 3 homogeneous case. So there's something about that proof that just cannot generalize. It can't possibly generalize. However, if a proof were given along these lines, my suspicion is it would generalize. And I think that gives sufficient reason to study this, to study a proof of something that we already, to find a proof of something, a new proof of something that we already know is true. Now, let me say, and really this is, I'm getting towards the end here. As I said at the beginning, this tree formula I've given is one of several, and there are several using reductions. There's a symmetric reduction, and then there's a tree formula for that, and so on and so forth. So I've given you a very short story here, but I want to mention this. Here's a formula, it's due to Heyman and Schmidt, that really gets down to the nitty-gritty. Instead of writing f as x minus h, let's write h out in bloody detail. Let's write it as the sum of monomials. So alpha is a multi-index. So this is a monomial in x. Its coefficient is p sub alpha. And since we're looking at the d homogeneous case, the degree of this alpha is d. And then g, formal inverse, also so given. And let's call this coefficients q's. Well, Heyman and Schmidt's formula gives the coefficient, the q's, as certain tree polynomials, a little different twist on it, certain tree polynomials in the coefficients p of f. And again, we want to show that the Jacobian matrix to the nth power equals 0 forces these coefficients q to be 0 in sufficiently high degree. In other words, to show that they're in the ideal or the radical of the ideal generated by the conditions that say JHN equals 0. Now, this approach is obviously more tedious than the one I've been discussing, for one reason, because there's a lot more indeterminates. You've got all these P's. There's a lot of them. But in this situation, we do have the confidence that what we are trying to prove is exactly equivalent to the Jacobian conjecture. In other words, we are not asking too much. So one question that arises, we want to consider the coefficients of these efficient polynomials, f1 to fn. Take those coefficients, the vanishing of those coefficients is exactly what says that JHDN is 0. So we ask, do those generate a polynomial ring, or I'm sorry, generate a prime ideal, or even just a radical ideal in the polynomial ring over C given by these PAs, P alphas. do they generate a prime or even a radical ideal in that polynomial ring? If so, the Jacobian conjecture is equivalent to showing the coefficients of in R are in this ideal for R bigger than our degree bound. And in any case, it's equivalent to showing that they're in the radical of that. So we're not asking too much. And one would expect, since these tree formulas involve dividing by things like alpha of t, and the Heyman-Schmidt involves factorials in the denominator, it doesn't stand a chance of working in any non-zero characteristic. And that's a plus, because we know the Jacobian conjecture is not true in the case of non-zero characteristics. So if such a proof can be given, even for the case d equals 2, I believe it would be very enlightening, and it might be the thing that opens our eyes and allows for a general proof. Now, of course, this is unexplored territory, and of course, we're haunted by the possibility that the Jacobian conjecture is not true, in which case we're all chasing down a rabbit hole, and that's why it doesn't work. But again, I emphasize, for d equals 2, we know it is true, and therefore some proof using this ideal membership approach must work. And such approach would not likely work in arbitrary characteristic. And so I think it would be a real breakthrough if that could be somehow uncovered. So there, I think I've got you to where I am right now. And I'm going to conclude my talk by saying thank you. Thank you to the organizers for the invitation to give a presentation. And thank you for your patience in listening. And as I said, I did put the notes in the chat. If you want to take a look at those, they're yours. And I'm going to stop the sharing. And we have a little time left before the next talk. So, Francisco, I'll turn it over to you. If there's any questions, I'll be happy to. I'll do my best.
Thank you. Thank you very much for a nice talk. So, guys, questions, please. Or comments.
Yeah, or criticisms. Those are also welcome.
So just open your microphone and
Hi, David. Thank you for the talk. So the D equals 2 case is magical, and it seems to work nicely. What makes the D equals 2 proof so nice that really doesn't extend at all?
So you can prove it very easily. I even thought about giving the proof in one of my slides. Since I had a little time, I probably could. It'll take you about 60 seconds. You write down a very simple trick with the Jacobian matrix. You use the homogeneity. You make a simple little preparation that the map preserves the origin, and you end up proving it. And the only thing the proof has is a 1/2 in it. But it uses the injectivity criteria. Okay, so it works in any characteristic other than 2. So the Jacobian conjecture is true in characteristic 3 or 5 or whatever for quadratic polynomials. And therefore, I consider that special, because you can take any polynomial map in any characteristic and do the degree reduction thing to get it to be identity plus cubic. You can do that for any. So therefore, we don't expect a proof of that case that works in as long as the characteristic is in 3. That's ridiculous, because that would be long. So everything about the proof of Wang's theorem has the number 1/2 written all over it, including Wang's original proof, which was different. That quick proof was given by a Japanese mathematician named Oda, and but even Wang's original proof, it involved dividing by 2. So that makes it very special. And also, the quick proof by Oda is quick. I mean, you see it, you believe it in an instant. But not only does it just divide by 2, it uses the injectivity criterion. So that makes it very opaque. I mean, how are you going to use that? You know, I have no idea, and I don't think anybody else does either. So yes, indeed, it is very special and very magical, as you say. I wish I understood it better, even though I can prove it to you in 60 seconds.
So, more questions, comments? And I have one. So, why do you believe that this new approach would transpass this problem of dividing by 2? I mean, because
So,
no, I mean, because you say that okay, you would like to prove the case D equal to using this new approach, and then you will have a general proof. Why do you think?
so the idea is to see formally why these tree polynomials can be written in the ideal or the differential ideal generated by whatever set of nilpotency conditions you want to choose. So any success that you have, so for example, in that D equals 2 case, when I should remember, there was the N4, the N5, the N6. I said I could use that method to show the N6 is equal to 0. Now, to me, it's a happy fact. That proof does not work, you know, in very many characteristics. It's got factorials all over the place in the denominator. So to me, at least the way I think, that's a good sign. So if one could see the formal combinatorial relationship, that's what I think would be enlightening. I'm looking for the magic formula. It's going to have factorials all over the place. It's going to show why the sum of trees of this height having this many vertices, when you break them down, you can see that they're in the differential ideals, say in these FRs that I showed you. And if that could be seen, even in the D equals 2 case, my instinct is you would see how to prove it in D equals 3 or higher D. And that's just a hunch I have. So you can shoot that full of holes, and I will stand here with my hands in the air because I can't tell you convincingly why that would definitely work.
Okay, thank you. So let's thank the speaker. It is different. So
that's the first online applause I've ever got in my life, by the way.
Yes, but you know, it's difficult. It's very difficult. Maybe the next conference in injectivities will be presential.